Hello everyone, and welcome to today's chem lesson. Today we're going to continue the discussion we had in our previous video about dissolving and what it means to dissolve. We're going to keep that going by introducing this piece of the reference table that you see on the screen here, Table F. And Table F is here to tell us whether or not a substance will dissolve. Before we jump in to talk about Table F, though, we are going to just take a small detour backwards to talk about dissolving again and what it means. When I have an ionic substance, right, if I have a compound like this that's positives and negatives, right, ions that are attracted to each other and held together by this magnetic force of attraction, and I put that substance into water, there are two options. The first option is the substance dissolving, getting broken apart by the water, pulled apart, and separated and surrounded by water molecules. This is what happens to things like salt when you put them in water and stir them up and you see them dissolve. In a situation where something dissolves, the strength of the water is greater than the strength of the ion attraction. Right? That means that the force that holds this positive and this negative together, the ion attraction, is weaker than the water. The water can come in here, isolate an ion, and pull it away to be surrounded and dissolved. The other option is something not dissolving. Right, settling down to the bottom of our glass of water and staying there. This happens when the water is weaker than the ion attraction. If the water isn't strong enough to come in here and pull the ions away, then the ionic substance is not going to break down. It's not going to look like this. It's not going to dissolve. And so the question that we need the answer to becomes, how can we tell if water is stronger than the ions, or if the ions are stronger than the water? And that is what Table F tells us. If we look at Table F, it is here to tell us which compounds are stronger than water, right? Which compounds have attraction that is stronger than water, and which compounds have attractions that are weaker than water. Right? Which compounds dissolve and which compounds don't dissolve. Which compounds are soluble and which compounds are not soluble. So, how do you read Table F? Looking at Table F, we see that there are two pairs of columns. The first set of columns right here, a visible gap between the two, and then a second set of columns here. The first group of columns shows us ions that normally form soluble compounds, right? Ions that can normally be broken apart by water. And we see there are a lot of options here. The other piece of the column is this exceptions piece. Exceptions, just like in regular life, do the opposite of what things normally do. So, for example, here's bromine. Right? A bromine ion is a bromide ion. if I have iron bromide, I normally have a soluble compound when I pair things up with bromine. Right? Bromine is soluble almost always. There are exceptions. Iron is not one of those exceptions. So this pair is soluble. But if I were to put lead bromide, I still have bromide, which is normally soluble, but lead is an exception. So it's going to do the opposite. It's not soluble anymore. It is insoluble. When we're looking at table F, all you need is to find one piece of your compound in the main column of either piece of table F. Right, in these cases, bromide was the ion that I found. And so I'm looking and I see, okay, I've got bromide. Bromide is normally soluble. It is insoluble if I'm with one of the exceptions. Iron bromide, soluble because iron is not an exception. Lead bromide, insoluble because lead is one of the exceptions. If I turn my attention over to the right side of table F, I see pretty much the same setup, but the opposite word being used. Right here, on the right side, we focus on things that are normally insoluble, things that normally don't dissolve in water, and their exceptions, the things that will make them dissolve in water. You should notice that there's a lot more text in the exceptions column on the right. But if you pay very careful attention, you notice that it's almost all the same text. Right? Every one of these says when combined with group 1 or ammonium. So really, that's just telling you that if you're paired with a group 1 or ammonium ion, you are soluble no matter what. And there's really only a couple of other things to look out for. Right, so what do examples on this side look like? Let's pick carbonate. Let's say I have iron, no, let's go tungsten carbonate. Carbonate is over here, right? I find it here. It's normally insoluble. Is tungsten one of the exceptions? Well, tungsten isn't in group 1, and it isn't ammonium. So it's not an exception, which would mean this is insoluble. What about something like lithium carbonate? Again, carbonate is over here, normally insoluble. Is lithium an exception? Well, yes, because lithium is a group 1 ion. So it is the exception to the rule, and so that would make this combination soluble. Let's see this with a little bit of practice on your end. Here we have 5 different compounds. One at a time, I want you to go through and see if you can tell me if these are soluble or insoluble. starting with sodium nitrate, NaNO3. Sodium nitrate is soluble. Right? If I want to find sodium nitrate, I can look for sodium. Sodium is soluble, no exceptions. If you missed sodium listed here and you found nitrate, nitrate is also soluble with no exceptions. So no matter which part of the compound you found, it is a soluble compound. What about iron chloride? Iron chloride is also a soluble compound. Iron doesn't show up in either of the main columns, but chloride does. Right here, you have your chloride. Chloride is soluble. Iron is not one of the exceptions, so this combination is soluble. Aluminum phosphate. Aluminum phosphate is insoluble. If I'm looking, I don't see aluminum in the main column on the left or the right, but I do see phosphate. Phosphate is normally insoluble. Aluminum is not one of the exceptions, so it follows the rule, and it is an insoluble combination. What about barium hydroxide? Barium hydroxide is soluble. I look, barium is not in the main column of either, but hydroxide is. Hydroxide is normally insoluble, but barium is an exception. So the exception to the insoluble rule is soluble. Lastly, silver chloride. Silver chloride is insoluble. Chloride is right here in the soluble column, but, not aluminum, silver is one of the exceptions. So the opposite of soluble is insoluble. This pair is an insoluble pair. One more question to drive this whole thing home. Based on the reference table, which of the following saturated solutions would be the least concentrated? Now, I couldn't fit the entirety of Table F onto this slide, so I pulled out the important piece. Sulfates are in the soluble column, just so you know. Right, this is taken from right here. Right, so we're in the soluble column and the exceptions. Which one of these things would be the least concentrated? In this case, the correct answer is choice 4. Barium sulfate would make the least concentrated solution. And the reason for that is that it is the only one that is insoluble. If we're talking about something being concentrated, we would want a lot of dissolved ions in it. These 3 all make soluble combinations with sulfate. So you put these in water and they dissolve. They put ions in the water and they form concentrated solutions. But barium sulfate, because it is insoluble, would just sink to the bottom of the cup and never dissolve, therefore making it the least concentrated solution. With that, I'm going to transition us over to our Google Meet for questions, comments, concerns, and attendance, and I will see you there.